Welcome to Next Gen Manufacturing Nexus. When we're talking about aerospace and high-performance automotive manufacturing, there is literally zero room for error. A tiny, almost invisible flaw can have absolutely catastrophic consequences. So today, we're diving deep into the race for perfection and the incredible technology that's actually making it possible.
Just look at these things. Machines like NASA's ISAC robot, they are right on the front lines, laying down these incredibly advanced materials with pinpoint accuracy. They are quite literally building the future of how we travel, one super meticulous layer at a time. But, with all that incredible speed and precision, it brings up a really critical question. Who is checking their work? How can we be 100% sure that every single one of those layers is absolutely flawless? The stakes here could not be higher.
So this isn't just a race for who can build things the fastest. No, this is a race for certainty. It's all about guaranteeing that every single part that comes off the line is perfect every single time. So what exactly are we up against? To really get why these new solutions are so brilliant, we first have to understand the nature of the flaw itself. Let's dig in. Okay, so at the heart of all this are what we call advanced composites. Now, these materials are just marvels of engineering. They're incredibly strong, but at the same time, they're feather light. Their big secret is their layered construction. But, well, that's also their Achilles heel. You see, as these carbon fiber tapes get laid down by the automated machines, tiny, tiny errors can creep in. We're talking about a slight gap here, a little overlap there, maybe a twist in the fiber, or even a stray piece of dust. To your naked eye, these things are practically invisible. And here's the kicker. This is the part that really gets me. Simulations have shown that these tiny defects can compromise a part's structural integrity by up to 32%. That is a huge loss of strength from a flaw that is almost impossible to spot with your own eyes. So with stakes this high, you'd think there'd be some super high-tech solution for quality control, right? Well, the traditional method is surprisingly low-tech and incredibly slow. Believe it or not, the standard way of doing this involves stopping the entire production line after every single layer is put down. A team of technicians then has to come in and meticulously inspect the whole surface with lights and magnifiers, just hunting for those tiny flaws. Now, think about a large aircraft part with, say, 96 layers. That means 96 production stops. You can just imagine the massive bottleneck this creates. It drives up time, it drives up cost. It's just not efficient. Okay, so how do we break this bottleneck? Well, the first big breakthrough is a real game changer. What if you could inspect the part in real time as it's being made? So let's take a look inside an automated fiber placement machine, or AFP for short. You see that heat lamp right there? Its job is to warm up the surface just enough so the next layer of tape sticks properly. It's a totally standard part of the process, but a really brilliant insight turned it into a powerful inspection tool. The idea is just so elegantly simple. You use the heat that's already there anyway. So as that lamp heats the base layer, a special thermal camera watches how that heat transfers into the new layer. It's basically giving the machine heat vision. And the physics behind it is pretty straightforward. Heat just moves differently through different thicknesses. So a gap creates a little thin spot that shows up as hot on the camera, while an overlap makes a thick spot that looks cool. Every single imperfection leaves its own distinct thermal fingerprint. And here is the proof right in front of us. On the left, you've got a diagram of a test panel where they intentionally created flaws. And on the right, that's the actual thermal image. The results are undeniable. Every single one of those defects is lit up clear as day. So seeing the defects is a massive step forward, but it's really only half the battle. You still need someone or something to analyze those images. And that's where the next big leap comes in: AI-powered quality control. The old way of doing this meant data scientists had to spend weeks, sometimes months, writing really complex code to analyze these images. The new approach? It uses an AI that can be trained in just a day or two. And not by a specialist, but by the actual manufacturing engineers right there on the factory floor. And this is all possible because of what's called a low-code platform. So instead of writing lines and lines of complicated code, an engineer can just drag and drop the image data to train the AI. It puts this incredibly powerful technology directly into the hands of the people who need it the most. It's a total game changer. So, when you combine this real-time thermal imaging with powerful AI analysis, you're not just improving a process. You are fundamentally changing the entire rulebook for how quality is managed.
Now, in a world as critical as aerospace, everything, and I mean everything, is governed by super strict quality standards. This one, AS 9102, basically dictates how manufacturers have to prove that a part meets every single specification. So any new tech has to fit within this really rigorous framework.
But what's really interesting here is that the standards themselves are actually evolving to embrace this new tech. The latest version of AS 9102 is shifting the responsibility for quality checks from the customer back to the manufacturer. And this is only possible because this real-time AI inspection provides the hard, verifiable data to prove with absolute certainty that a part is flawless. And this all brings us to a really fascinating question. We're creating systems that can see things that we can't and can process information faster than we ever could. So as this technology becomes more and more widespread, are we approaching an age where manufacturing defects just become a thing of the past? Makes you think, doesn't it?